particularly Dr. Gurpreet Kaur. She has completed her master's in physical chemistry from University of Jammu. She has done MPhil in physical chemistry from University of Jammu. After that, she qualified her PhD from Queensland University of Technology, Brisbane, Australia. And presently, she is working as a research assistant in University of New South Wales, Sydney, Australia. She is working on the topic of first principles investigation on transition metal-based electrocatalyst for efficient clean energy conversion. Welcome, Gurpreet ma'am. Over to you.
Okay, my name is Gurpreet Kaur, as introduced by Dr. Gurpreet Kaur. So I am here. I would like to share my recent publication that just got accepted in Journal of Material Chemistry A. So I'm just sharing only one work. That's a computational screening of single atom alloy. That's for enhanced electrochemical nitrogen reduction reactions. So here is an overview of my presentation. I'll be talking about introduction, followed by computational details, and then I have results and discussion, and at the end, I have conclusion. So, sorry, I should put that in here. Okay, yeah, so here it's a nitrogen cycle. Most of us are very much familiar with the cycle where nitrogen, which is otherwise inert because of a very high triple bond, that cannot be used as such. So it has to be converted to various usable forms for plants and other microbes. So nitrogen cycle in here, the nitrogen is converted to ammonia in presence of nitrogen fixing bacteria, and also in presence of lightning. And then the ammonia is converted to nitrate using nitrifying bacteria. And at the end, we have denitrification, where nitrate is converted to nitrogen. So nitrogen moves from the atmosphere to terrestrial to marine ecosystem in different chemical forms. So here we are very much interested in this process where nitrogen fixation, nitrogen is converted to ammonia. So this is a biological process or natural process of fixing nitrogen to ammonia. So, and also on industrial scale, we have Haber-Bosch process where nitrogen is converted to ammonia. But this process is taking place at elevated temperature and pressure, very high temperature and pressure. And this process, there are certain drawbacks of this process, like it's highly energy intensive. In addition to this, we have this process that leads to the emission of lot of greenhouse gases. So it's very important to look for the alternatives of this Haber-Bosch process. So there is a one alternative, that is a electrochemical reduction of nitrogen. It has certain advantages, like this process can take place at normal temperature conditions of temperature and pressure. And here the catalysts that are electrocatalysts, they play a very important role in converting nitrogen to ammonia. So here the electricity can be obtained from the various renewable energy resources. So here in the research, a lot of research is being done to increase the efficiency of these electrocatalysts. So a number of catalysts are there, like there are a number of metal-based catalysts, non-noble metal-based catalysts. We have metal-free catalyst as well, and single-atom catalyst. And in sometimes doping is done to increase the efficiency of these catalysts. So here it's a volcano plot. I got this figure from one of the papers by Norskov. He's very renowned scientist in the field of electrocatalysis. So they studied the various transition elements, both in the flat surface as well as in the stepped surface, for the conversion of nitrogen to ammonia. And we can see in case of stepped surface, the conversion of nitrogen to ammonia, the first hydrogenation step is the rate determining step. So the conversion of nitrogen to N2H. So that's a rate determining step for most of the transition elements. And the ideal catalyst should be on the on this line. That's the equilibrium potential, having zero over potential. And we can see that in this case, the ruthenium is occupying the top position in this volcano plot. So, the ruthenium, it's considered as one of the best electrocatalysts for nitrogen reduction reaction, and it has been extensively studied both computationally as well as experimentally. But it has high overpotential of 1.08 electron volt. So there are certain challenges associated with these electrocatalysts. Like most of them, they show very high overpotential for the conversion of nitrogen to ammonia. In addition to that, they have low selectivity because there is another reaction taking place. That's a hydrogen ablative reaction where the proton will interact with another molecule giving hydrogen, H2. So that will lower the efficiency of these catalysts. So here are the various pathways for the conversion of nitrogen to ammonia. So we have the first is the dissociative pathway, where the nitrogen, after getting adsorbed on the surface of the catalyst, undergoes an N bond cleavage, and the remaining nitrogen, upon hydrogenation, it converts nitrogen to ammonia. And in addition to the dissociative pathway, we have associative pathway, where the nitrogen can either adsorb in end-on configuration or in side-on configuration. Like in case of end-on configuration, only one nitrogen is forming bond with the catalyst. However, in case of side-on configuration, both the nitrogen, they form bond with the catalyst. And both of these end-on and side-on configuration, they have two further different mechanisms. Like we have a distal mechanism, we have alternating, and here is enzymatic, and this one is consecutive reaction pathway. In case of distal mechanism, both the nitrogen, they are hydrogenated one by one, giving rise to two molecules of ammonia. However, in case of alternative reaction mechanism, only one nitrogen, the one nitrogen that is far from the catalyst, that is hydrogenated, converted to then this is converted to ammonia, and the remaining nitrogen upon further hydrogenation gives another ammonia molecule. However, in case of enzymatic, we have enzymatic and we have a consecutive reaction pathway. These are this distal is very much similar to the enzymatic, and alternating is very much similar to the consecutive pathway. So in our work, we studied all these reaction pathways. So why it's not going next? Sorry, it's not going next. Hello?
Hello, ma'am.
My presentation is not going next. I'm not sure. Okay, now, yeah. Sorry for the interruption.
No issues.
Sorry. So here's a motivation for my work. There was a recent work where they have studied the platinum single atom alloy for the conversion of as an electrocatalyst. So they found that platinum and platinum single atom alloy, they were supported on nitrogen doped carbon nanotubes. They have quite high efficiency and like good performance as compared to the platinum, as compared to the commercial platinum on the carbon. So they found that the single atom alloy, they performed very well. And another work where they reported a single atom alloy based on gold 111. So they doped the surface of gold with the transition elements, the whole series of 3D, 4D, and 5D transition elements. And again, they found that the single atom alloy have shown good results as compared to gold 111. So we came up with an idea that, like, we know that ruthenium has performed well. So we but it has quite high overpotential. So we tried to study the single atom alloy based on ruthenium, and we doped the top layer of ruthenium with the 3D and 4D transition elements. So here is a methodology for my work. We used a Material Studio. I used VASP for carrying out all the calculations, and Vesta to analyze the various results. And the geometry optimization was done, free energy calculation was done, Bader charge was carried out, and I also carried out the ab initio molecular dynamic simulations to study the thermal stability of the catalyst. And climbing image node elastic band method was used to calculate the kinetic barrier of the various reactions. And then at the end, we also used microkinetic modeling to calculate the turnover frequency for our catalyst. So here is a structure of the catalyst that is based on ruthenium 0001, and we doped the top layer of the ruthenium 001 with the 3D and 4D transition elements. We also calculated the energy of different doping sites, and we found that almost all the doping sites, they have very much similar energy. So we just considered one. So for the study of these catalysts, we have certain criteria for the best catalysts. So the first, based on the experience we have like reported in different papers, we have the free energy change for the nitrogen adsorption. It should not be positive, and it should be less than 0 electron volt. And the second criteria is the first hydrogenation step, because in almost all the cases studied so far, this step is considered to be the potential determining steps. So that's the highest energy step. So it should be less than 0.50 electron volt. And in addition to these two, it's also important to study the selectivity of NRR over hydrogen evolution reactions. So based on the first criteria, we plotted the free energy change for nitrogen adsorption on this ruthenium 001. That's a single atom alloy. And we found that, so based on this first criteria, we found that this titanium, vanadium, chromium, here we have niobium, molybdenum, and also we considered rhodium because it's quite close to this line 0 electron volt. So we considered these electrocatalysts for the further study. So then the second criteria, that's the free energy change for the first hydrogenation step. So we plotted the results for this step, and here based on this second criteria, we just selected vanadium both in end-on and side-on configuration, as well as titanium in this side-on configuration, because there the free energy change for the first hydrogenation step was lower than 0.50. And also we calculated the hydrogen evolution reaction for vanadium doped and titanium doped ruthenium 001, and we found that the free energy was quite negative, like highly negative. So it's very, so here this HER is quite suppressed as compared to NRR. So in addition to thermodynamical aspect, we also calculated the kinetic barrier for the hydrogen evolution reaction. And we found that in each case, the kinetic barrier was over 1.50 electron volt. So quite high. So here that means for our catalyst, the HER is quite suppressed. So it's not reducing the activity of our catalyst. So here is the nitrogen adsorption on the surface of vanadium doped ruthenium 001. And here we can see that the nitrogen, in case of this side-on configuration, gets elongated from the value of 1.098 angstrom to 1.17 angstrom. And in case of here, end-on configuration, again, there is an elongation of nitrogen on the adsorption of nitrogen on the surface of this catalyst. So that means there is an active adsorption of nitrogen on the surface of vanadium. And similar, we calculated the energy for the nitrogen adsorption on titanium-based ruthenium 001. And they have very quite similar results as similar results to that of vanadium doped ruthenium 001. So further, we studied the Bader charge analysis, and we found that there was a charge transfer of 0.56 and 0.54 in case of vanadium, and here in case of titanium in side-on configurations. Whereas in case of end-on configuration, there is a less charge transfer. So that means the nitrogen adsorption in case of side-on, it's highly like negative, and it's good for further analysis. So that means the catalyst in side-on configuration, they have higher activity than in case of end-on. So further to that, we calculated the density of state for both the pure ruthenium and the doped ruthenium. So here on the left, we have ruthenium, pure ruthenium with the nitrogen adsorbed on the surface. And here is the nitrogen adsorbed on vanadium doped ruthenium 001. So here in case of pure, we can see that the unoccupied pi star orbitals, they are vacant and they are very much far away from the Fermi level. However, in case of doped vanadium doped ruthenium, we have this these unoccupied orbitals, they are now occupied and they are lying close to the Fermi level. So that means this doping of ruthenium with the transition element, this has enhanced the adsorption of nitrogen on its surface. So that means this single atom alloy, it's working. So here, further to that, we calculated the free energy diagram for vanadium doped ruthenium 001 for consecutive pathway. So it's a thermodynamical pathway where the nitrogen, after this side-on adsorption, it has a adsorption energy of minus 0.02 electron volt. So this whole process, it consists of 6 elemental steps of proton-coupled electron transfer from nitrogen to ammonia. So here we found that the first, after the adsorbed nitrogen, it reacts with one pair of electron and proton and give rise to the formation of NNH. And the free energy change was 0.15 electron volt. So this was the highest energy change that was encountered as compared to the whole process. And then in the next step, the NNH was further hydrogenated, giving rise to the formation of NNH2. And the free energy change was minus 0.49 electron volt. So here, all the steps, they are downhill only, except for this, the first step and the conversion of N to NH. So they were the uphill steps. And so after the elimination of one ammonia molecule, the remaining nitrogen upon further subsequent hydrogenation gave another ammonia molecule. So here we found that the potential determining step was accompanied by the free energy change of 0.15 electron volt. So from that, we calculated the limiting potential, and the limiting potential was found to be minus 0.15 volt. So that's a very low negative value reported so far for nitrogen reduction. And these are the various structures of the reactive intermediates that were formed during the whole process. So in addition to this thermodynamical aspect, we also calculated the kinetic barrier using CI-NEB method. So here we found that in case of vanadium doped ruthenium 001, the kinetic barrier was found to be 1.14 electron volt, corresponding to this PDS, that's a potential determining step. So here and this kinetic barrier is quite low as compared to the pure ruthenium. In that case, this kinetic barrier has been reported as 1.85 electron volt. So, And so that means the single atom alloy of vanadium doped ruthenium-001, it has decreased the kinetic barrier for PDS drastically. So here is the enzymatic pathway where the nitrogen in the side-on adsorption, again following the different hydrogenation steps. Here we found that this step was a potential determining step, and the free energy change for this step was 0.30 volt. So this was the highest energy change for the whole process. And here again, two ammonia molecules were formed upon hydrogenation during the whole process. And these are the various reactive intermediates formed during the process. And here the kinetic barrier for PDS, so that's a potential determining step, that where the NH2 to NH2 that corresponds to 1.51 electron volt. And the limiting potential for this process was found to be minus 0.30 volt. And here we have alternative, and this is the distal reaction pathway. So here again, the adsorption was quite like it's negative, but we found that the first this step, that's a conversion of NH to NH, was quite high in energy, that is 0.89 electron volt. And in case of distal mechanism, the first hydrogenation step was found with the PDS, and the free energy change for that step was 0.50 volt. So out of the four different pathways, that's the distal, alternating, enzymatic, and consecutive, vanadium in case of consecutive pathway has given a better results, like good results with quite low negative limiting potential as well as low kinetic barrier. So in addition to vanadium, we also selected titanium for further analysis. Here, it's an enzymatic pathway and it's a consecutive pathway. The reaction pathway are very much similar as we studied in case of vanadium doped ruthenium-001. But in this case, the first step, that's a hydrogenation step, the adsorbed nitrogen in the in the side-on adsorption, the first step, that's a conversion of NNH to NNH was quite high, that is minus 0.47 volt. And similar was the case in case of consecutive titanium. So in further, the catalyst stability is also very important aspect. It's very important to study the thermodynamical stability of these catalysts. So here we have the AIMD calculation for both the vanadium and titanium, and where we can see that there was not much energy variation during the increased temperature, like we have a temperature up to 2000 Kelvin. And so there was and also after the calculations, we found that the initial and the final structures, the geometry was quite similar. There was not like very much buckling of the structure. So that means the catalysts, they have a quite high thermal stability. So here the figure, the contour plot, they shows the turnover frequency. That's a very important factor to analyze the activity of a catalyst. And here we calculated the turnover frequency at the temperature range of 500 to 1000 Kelvin, and the pressure ranging from 0 to 100 bar. And here we found that the turnover frequency was 4.25 10 raised to power minus 3 per side per second, which is again quite low as compared, quite high as compared to the pure ruthenium, where the turnover frequency is of the order of 7 into 10 raised to power minus 5. So And here, this graph shows the variation of turnover frequency with the temperature. So as we increase the temperature, turnover frequency increases. And here is a variation of pressure with the turnover frequency. So with the increase of pressure, again, the turnover frequency showed increase. So that makes sense, because as we increase the temperature, so that helps in overcoming the kinetic barrier. And with the increase in pressure, the molecules will be close enough so they can interact and get converted to ammonia. So here are the conclusions for my this work. So we investigated the potential of various 3D and 4D transition metal doped ruthenium 001 for the nitrogen fixation process. So here we selected vanadium doped ruthenium and titanium doped ruthenium for further investigations, depending on the various because of those selection criteria, we selected these two for further studies. And we found that vanadium doped ruthenium 001 that showed excellent performance with a quite negative low limiting potential of minus 0.15 volt for the ammonia formation following consecutive pathway. And the titanium doped ruthenium 001 also showed limiting potential of minus 0.47 volt for the ammonia formation by both enzymatic and consecutive mechanism. And in the last, the turnover frequency was found to be 4.25 10 raised power minus 3 per site per second at 700 Kelvin and 100 bar pressure. So I would like to thank my professor, my group members, and all the computational sources, HPC, NCI, POS-A, and thank you all for your attention. So I would like to thank all of you, all the audience. I'm happy to answer now.
Thank you, Guru Krishna. Thank you very much. Anybody from the participants want to ask anything?
I have one question, Dr. Gurpreet.
Yes.
So, how you prepared the single atom alloy catalysts and how you characterized, because there is not much difference between a single atom catalyst and a bulk catalyst when you prepare. So, what was the procedure which you followed, and then how you characterized that this is a single atom alloy catalyst?
So first, this is like we have done this computationally, not experimentally, but there are certain research papers have been reported so far. So they are following certain techniques to make single atom alloy. So this is just this is a DFT modeling. So there are papers.
These are already prepared catalysts. You take them from literature method, already prepared catalyst, and then you.
So I showed one paper where they have prepared this. Gold based single atom alloy. So that's the experimental work as well as the computational, where they are doping the surface of gold 111 with the transition elements. So I haven't read the experimental techniques to prepare that, because we are doing DFT modeling, but it is feasible to prepare that experimentally.
Because as far as I know, high temperature is required to prepare these single atom catalysts. For example, 900 degree or above that. So
honestly,
okay.
I haven't read.
Yes, you already told me you are
I haven't
dealing
read
with
the experimental
computational part
techniques.
only.
Yes.
Okay.
Yeah.
Okay, thank you.
I think Jasper want to ask anything. Jasper, do you want to ask something?
Yeah, Dr. Gurpreet, it was a nice presentation from your side. I liked it very much. Could you please tell me that what would be the effect of physical adsorption on the energy profile? Because you have shown the chemical adsorption of nitrogen on these catalysts. And what could be the effect of the physical adsorption of these nitrogen molecules on the surface, on the energy profile?
Yeah, so in case of physical adsorption, the adsorption energy would be very low, right? So when the nitrogen is being adsorbed chemically, so that's the adsorption is negative. The free energy change for the nitrogen adsorption is negative. But in case of physical adsorption, that's a very low adsorption. We haven't considered that because, for the catalyst to be for a good catalyst, there should be a good adsorption of nitrogen. So for converting nitrogen to ammonia, we consider only the chemical adsorption, like the strong adsorption of nitrogen.
Yeah, what does the experiment show as far as the adsorption of nitrogen on these catalysts is concerned? Is it undergoing the chemical and physical adsorption simultaneously following the Langmuir adsorption isotherm or the BET adsorption isotherm?
This in this case, it was chemical adsorption because the adsorption energy was quite low. That was minus 0.5. So that is considered as a chemical adsorption. So there were quite a number of I studied 20 single atom alloy, so 3D and 4D in total. So there were some catalysts that was showing physical adsorption, but we haven't considered those cases. We just considered those with a high adsorption.
Okay, thank you very much. Thank you.
Thank you.